Alternatively, we can talk about phi star. And last time, you showed that the Lagrangian of the two are actually equivalent, right? And so the Lagrangian of the two real scalar fields has exactly the same form as the Lagrangian density of the phi star. The explicit form of the Lagrangian of the complex scalar fields is given as you can see. Okay?
Yes.
Now we talk about transformations. And any problem? Everybody with me?
Yes.
Okay. So we can talk about the transformations, and whatever transformation we do to the real scalar fields, like this figure, we have phi 1 and then phi 2, and then we can rotate it by an angle alpha. And mathematically, this type of rotation can be written like this. So on the right side, we have phi 1, phi 2, and we have a 2 by 2 matrix, which acts on phi 1, phi 2, and the left-hand side is the rotated. So that's what happens in the left-hand side. Now, we said that the two Lagrangians are equivalent, and we asked ourselves the question last time, if it looks like, what happened? Oh, okay. If it looks like a rotation in scalar fields, then you calculated last time that the rotation for the two real scalar fields translates into something like a phase shift when you talk about phi star, right?
Stop.
Okay, everybody still with me?
Yes. Yes.
Where alpha is the rotation angle. So I'll go to the next page. So those are the transformations that we would be interested in. Okay. So anyway, this is the result. The two equations encircled by the in red. This would be the phase shifts. And when we say transformation of the phi matrix of the phi fields, it's actually some sort of a phase shift. Okay. The two lines above are just the calculations that could be done. Essentially, you know, if you start with phi and you transform it, you go to some phi prime. What is this square box with a question mark? And so you do some calculation and you arrive at this expression. So you did that last time, right?
Yes. Yes.
Okay. So if you did that, let me erase this page. Then we go back to our Lagrangian density for the complex scalar fields, the phi star, and then apply the transformation. That means you put a prime for phi, a prime for phi star, and then a prime for phi star and phi. And then for the phi prime, you plug in the e to the I alpha phi. That means you subject the phi by transformation going to phi prime, and you do the same for the phi star. So since alpha is a constant, it would just slip through the derivative, this partial of mu, so it goes out of the derivative. And for this expression, the phi prime star, the exponential of that would just, you can take it out of the derivative because alpha is constant. So the two exponentials would just cancel, e to the minus alpha and e plus I alpha. And the same with the second term, where the exponentials just cancel. So with the cancellation of the exponentials, the transformed Lagrangian will reduce to the original form. That means you are left with partial of mu phi here, and then partial of mu phi star here. And for the second term, it's just mass squared phi star phi. Okay, so the Lagrangian, even if you transform it, you still obtain the old form as before, same L as before. Okay, so then we say that the Lagrangian density is invariant under the transformation. And so we look at the changes. So we say that the difference, the delta L, between the Lagrangian before the transformation and after the transformation is equal to 0. Because L prime minus L has the same form, and you subtract, so you get a 0. So delta L is equal to 0. And if we would like to know what type of infinitesimal transformation, because normally in all of these gauge theories or Yang-Mills theories, you only talk about very small alpha, very small transformations. So if you would like to know the form of delta small transformation, then we go back to the expression for the transformation. That means phi prime is obtained by e to the minus I alpha. And since alpha is very small, then you can expand the exponential. So the exponential e to the minus I alpha is just 1 minus I alpha plus alpha squared plus alpha cubed. But the alpha squared and alpha cubed we could ignore because alpha is small. So this can be written in terms like this. So if you multiply by phi, the 1, you get this term. If you multiply by phi, this I alpha, then you get this second term. So now, if you transfer this phi to the left-hand side, so left-hand side has phi prime. So phi prime minus phi, what is left on the right-hand side is just this minus I alpha. And so the small changes of scalar field phi, the delta phi, which is the difference of the old and the new, has this specific form minus I alpha phi. We need this delta phi expression because when we calculate for the conserved currents, the conserved currents would have this. So we could actually substitute in the conserved current this minus I alpha of phi. And we can do the same thing for the phi star. Which means that you get phi prime star by letting e to the I alpha multiplied by phi star, expand the exponential 1 plus I alpha, and then multiply phi star with 1 and phi star with I alpha, and then transfer to the left hand side the phi star. So on the left hand side, originally you have only a 5 prime star, then you have minus 5 star, which came from the right, then what is left on the right hand side is just I alpha 5 star, and that's what you call delta 5 star. Now, when we discuss the Noether's theorem, we had, let's see, oops,
Yes.
okay, maybe I can raise this. This is the bottom of the page. So normally the conserved current is of this form. So in the relation, since now we have two fields, phi and phi star, here we have the delta phi, and we just computed that a moment ago. And we also have a delta phi star, and we just computed that a moment ago. In fact, the result of that was something like this. Delta phi star is this, and delta phi is this. So you just plug that in, and you did that in class, right?
Yes, yes, no.
Yes. Okay, and you did that in class, and what you got is the expression for the conserved current. Let me just fix this.
Ay, excuse me, Doc.
Yes.
Nag-notify yung Zoom na mag-e-end yung meeting in 10 minutes. Kasi daw, ano?
Okay, so we can reconnect, right?
Yeah. I guess so.
Okay.
Pero,
So,
Adrian, nakay idea ani? Back.
What do you mean ID? What do you mean
Idea. Like, ano ba? Masasabi mo. Nakatry na ka ani na mag-end ang meeting.
Wala pa.
Within 40 minutes. 40 minutes lang kasi. Tapos sabi niya, upgrade to Pro. Yung Zoom.
okay. No problem. Let's take care. Let's just make use of the free one. If they cut us off in 10 minutes, then that's fine. At least we have testing already.
Sige, Doc. Mag-create lang ako if ever.
Yes, and then just text na lang para we can check whether we continue a little later or continue some other day.
Okay,
We'll play it by ear.
Okay, Doc.
Okay, so we already have this form for the conserved current for scalar fields. And we also discussed for Dirac fields, right? We already have a form for the Dirac field given by this one. And then the expression for the conserved current when we discuss Noether's theorem is given by this one. Oops, sorry. Okay. And again, you have a delta psi, and you want to know the form of delta psi. And you can do that by going back to the transformations that affect the psi and psi bar. So again, you get psi prime by multiplying e to the IE alpha, then expand alpha, and then multiply, and then you'll get this form of the IE alpha psi. And you do that for the complex psi bar also, complex conjugate. So you get a form of del psi and delta psi bar. And then you got this last time. Is that correct?
Yes.
Okay. You have that expression for the Dirac current. Please try to remember always the form of this Dirac current. That means J mu is equal to minus E is the charge, psi bar gamma mu psi. Okay, always psi bar gamma mu psi. Every time you see psi bar gamma mu psi, then that's just the Dirac current, because you will see it often in this course. So let's move on. let me see. I skipped some pages. Okay. Okay, let's talk about U1 gauge invariance. Okay, you can see the page, right?
Yes.
Okay, let's go back to our Dirac-Lagrangian given by this. And then we apply a global gauge transformation. Global means that the alpha that you place in the e to the I alpha is constant. It's the same everywhere. So the alpha used by Adrian is the same as the alpha used by a Japanese physicist. Everywhere, it's not a function of space and time. And then take the complex conjugate of that. Then you have also a transformation for the psi bar. Then you go back to your Lagrangian and you say that you transform psi and psi bar. That means you put a prime everywhere, psi bar prime, psi prime, psi bar prime, psi prime. So, and then you plug in this expression. So what happens is that for psi bar prime, we have this e to the minus I alpha psi bar. You have a gamma mu, partial mu, and the psi prime is just e to the I alpha psi, as you can see here. And minus m psi bar prime psi prime. So this is psi bar prime, this is psi prime, and clearly you see that the exponentials would cancel out. And since alpha is constant, then it would slip through. You can take it out of the derivative. And so the two exponentials, e to the minus I alpha and e to the plus I alpha, would also cancel out. So what happens is that under the transformation, your transformed Lagrangian L prime becomes, we have an I psi bar gamma mu partial of mu psi, and then here minus m psi bar psi. It's exactly the same form as the original untransformed Lagrangian density. So we say that the Lagrangian is invariant under the global gauge transformation. Now, the next thing that you can do, and if we are cut off by Zoom, you can try the transformation where now this time alpha is a function of space-time. So you go back to the original expression of the Lagrangian, say something, where's that? This one, okay? And then put a psi bar prime, psi prime, put a prime in all the psi bar psi, but now the transformation has an alpha which is dependent on time, on space-time, like this. So why don't you try it? Because 40 minutes is almost up. Ilang time pa ba, Anwar?
2 minutes. No?
2 minutes.
2 minutes. Okay, so I leave you with a question. Is the Lagrangian density for the Dirac-Lagrangian invariant under local gauge transformation? Local gauge transformation means that alpha is a function of space and time. So alpha function of x. And the transformation looks the same, just like the global. The only difference is that alpha is now a function of x. Okay? So when we zoom again, either later if it's allowed, tell me if it's invariant, and if it is not, tell me if you have any suggestions how to remedy the situation, because physicists would like invariance. They want these mathematical objects to be symmetric, invariant, under any type of transformation. That means invariance means there is something preserved according to Noether's theorem. So that's all for now. You calculate and try to answer the question whether the Dirac-Lagrangian is invariant under local gauge transformation. Have I discussed this?
Not yet, Doc.
Yes, Doc.
Yes.
A local
Not
gauge.
yet.
Not yet?
Not yet.
Okay, so let's connect later. Thank you very much.
What
Just
time?
Hello.
just fiber. Thank you. Bye.
Okay, Doc.